And I am talking about minimizing noise during fMRI acquisition. So I'm going to start out with sort of one of the challenges that's both for me as a teacher of this subject, and I think for a lot of people trying to grapple with this topic as researchers. And as I was preparing for this talk, I came across a quote in this brand new paper. The paper is titled "Impacting the Effect of fMRI Noise Through Hardware Acquisition Choices." And I'm actually not going to talk much about this specific paper, except the first sentence of the introduction of this paper jumped out at me. It says, applied to intensity fluctuations of a pixel in fMRI time series, the term noise is so nonspecific and carries such negative connotations that it should probably be eliminated from the fMRI vocabulary. So what I love about this is it says, they're very honest with their opinion about the word noise, yet they still put the word noise in the title of their paper. So they're both simultaneously acknowledging that it is a terrible, horrible, complex word, but they can't live without it. And from the teaching perspective, I think that means that I can't teach you everything about fMRI noise. If I was doing that, if to teach everything about fMRI noise would be essentially an entire course in MRI physics plus. And from the research perspective, thinking this through, a lot of the more unpleasant disagreements in this field of fMRI methodology have come down to saying, someone saying my method best reduces this type of noise, and someone else says, yeah, sure, you reduce that type of noise, but at the expense of some other type of noise, which you really can't ignore. And so many disagreements are essentially coming down to what type of noise do people care about less or care about more. And, in some of the talks in this series and some, my talk today, it's like, do you care about motion-related noise? Do you care about scanner noise? Do you care about, there's all sorts of noise. So that's one thing to keep in mind, is that there's no clean answer of noise, and there's no clean answer of what it means to reduce noise. Except maybe you'll know it when you see it. So what do we mean by noise? Noise is, there's going to be measurement noise. So thermal noise is sort of the pure physics of the system, in any sort of system, what measurement error is. And then you have imperfect image reconstruction. So, how we reconstruct image is not like a flawless situation. You have undesired signal fluctuations. So there's breathing, pulsation. I should note that it's not undesired that your subjects are breathing, but it would make our data a whole lot cleaner if they weren't. There's head movement, chest movement, task non-compliance, unmodeled neural effects, unmodeled aspects of likely hemodynamic response. This is all noise. And sort of this measurement and these undesired fluctuations kind of merge together in what's called temporal signal noise or contrast noise. So that's the difference between sort of, does an image look good versus does a time series convey the information, contain the information in what I wanted to see and with a strong signal. The other thing to keep in mind is one person's noise is another person's signal. So the cleanest example of this is if you're doing a task-based data, any neural variation that isn't your task is noise. If you're doing a resting state scan, where you're looking at correlations between areas, anything task correlated is, anything that you can model is annoying, and sort of that the correlations that drift on top of that are what you care about. So with that opening, I'm going to divide this talk into 3 different sections of how to think about noise. And in each of these topics, I'm not covering really anything in depth, so you can ask questions or we can talk later or offline, but I'm just trying to give you a sense of different ways to think about noise during acquisition. And I've divided up into preventative scanner health, so what do you do in general to make sure that the equipment you're using is collecting good data? And that's both, information that someone maintaining a facility would do, but also someone who's just a user actually should care about this stuff. Things you do to noise that relate to sort of peripheral measurements and your participants, and things relating to parameters and pulse sequences. So for preventative scanner health, I've divided into regular quality assessment, regular overall evaluation of your results, and real-time data observation. So just as an example of QA scans, this is what's done here. Approximately daily for every scanner and every commonly used head coil in the scanner, we're collecting with a phantom, so sort of a jar of oil every single day, a pretty basic sequence, EPI, consistent grid, voxels for 5 to 10 minutes. And we're saving those time series. Sometimes we'll save the raw data too. And just looking at that over time to see how it varies over time. So as an example of what the QA scans look like, this left plot is temporal signal noise, which is essentially the mean of your data divided by the standard deviation of your data. So the higher the mean versus, so for a jug of oil, you don't expect your signal to change over time. So essentially, the larger the mean is versus the standard deviation, the better temporal signal to noise you have. So what you can see in all these scanners is they're mostly flat. Sometimes you see weird things happening. When you see a weird thing like this, it's more likely something wrong with the QA scan that day as opposed to a scanner issue. But sometimes you'll notice things that actually are an issue. And for some of our scanners, we're actually collecting these TSNR plots for every single receiver coil. And you can see that there is variation among those receiver coils. And in some cases, you might have a failed coil, and this would highlight it. So this is sort of happening from the high-level point of view, but anyone could look at these data and keep track of them. The other thing you can do, and it's been automated a bit more recently, is regularly evaluate your results. So here's a fairly recent software package called fMRI QC, which has a nice thing of running a bunch of quality metrics on your data. And in addition to running the quality metrics, it can throw them into a distribution of other data from similar scans. So this specific plot I pulled is from an anatomical quality control. And this is sort of the distribution. Each dot here is an individual session. So if you see a dot up here, you could say, okay, why is that one so far from the distribution? And you can click on it and look at that subject more carefully. And the reason this is important to users is if you're collecting data and your data is just off, is away from what other people are collecting, that's your first warning sign that you're doing something wrong. And the worst case scenario, and I wish I'd say I've never seen this, is someone collects a study's worth of data and then discovers that they've misset a parameter. And that entire data set is garbage. So regular evaluations are a critical part to keeping, controlling noise during acquisition. And that's something that really relates to everyone. Sometimes more important, and sometimes if you're not paying attention, things can get pretty unpleasant. The last part of regular evaluation is when you're collecting data, just look at it. So on some of the scanners here, we have this AFNI real-time setup, which is a lovely way to keep track of it. So you're seeing the data coming in real time. You're seeing the motion parameters, and you're seeing the time series for a given location on the screen. And as you're going, you see that person's head move. And your options there are to recollect that data, or more important, tell that subject, maybe you should try not to move your head quite as much during the next session. And you can see it sort of following through. But as I'll stress more later, a lot of quality control is interactions with your participants. So if you're seeing things like this, and it looks like the subject constantly does this, you can either cut your losses at the scan or really talk to them and try and figure out what's wrong. It's better to take a subject out, readjust their head padding, and put them back in than collect 2 hours of data with motion of this magnitude. The other thing with real-time measurements is you can get a sense of what your artifacts are in a specific data set. So here's an example of here's respiration traces. And if you click on a correlation of an area, you can see that location has some similarity to respiration traces, and everything sort of, in this case, like large vessels and maybe some ventricles are highlighted. So they're highly correlated with your correlation point. And this is using a nice tool in AFNI called instacorrelation, which you can use any point in the system, so you can use immediately after the scan, or you can do this as a scan is being collected to get a sense of what's correlating. And that's also particularly useful if you're seeing systematic variations. So you see a scan like this, you look at a location here and you see a signal drop here. Now this is not a huge signal drop. So like if I just showed you this time series, you say, I wonder what's happening there. but it wouldn't bother you too much. But if you sort of expanded the field of view and looked over a much bigger area, you'll see that the exact same big drop is over a lot of tissue. And again, we can use this intercorrelation tool to see that this big drop is correlated spatially. So it's not correlated, it's not just gray. This is like a white matter map. You can see it crosses gray matter, it crosses white matter. It crosses quite a large region. So if you're looking at your data as it's being collected or soon after, you could say, okay, there's something really wrong here. And in this case, this was one of the receiver coils was failing, and it was causing a unpredictable fluctuations in signals that was sort of took a while to trace and locate. And this was one of the tools that was eventually useful in helping locate it. So that was sort of this beginning area on sort of scanner maintenance. The next big section I'm going to cover is peripherals and participants. And like I said, I'm going to sample a little bit here and a little bit there. For peripherals, I'm primarily going to focus on recording respiration and pulse and a little bit on eye movement. Areas that I'm not really covering for the peripherals part are head movement and other types of recording. So I'll mention a little bit about head movement later, but for other recording, we often think of multimodal imaging. You're collecting EEG, you're collecting, scalp, galvanic skin response, which is another neural measure of attention or arousal or fear. And we think of these as just additional signals, but you can also think of these as ways to control your noise, because everything you can model in your data is another way to be confident what is signal and what is not signal. For participants, I'll be talking about head restraints and just other ways to work with your volunteers. I should also say, feel free to interrupt if you have questions along the way. So for respiration and pulse, my next bunch of slides, I am being a consistent title because I want to drive this message home, which is collect respiration and pulse data. There are a lot of tools in post-processing, which some talks in this series might bring up, that help you remove respiration and pulse data. So there's these methods called retro-ICOR, respiration following over time, heart rate variation. You can look all these up. These are ways to use respiration and cardiac traces to sort of clean up your data post-processing. And I've heard a few times, well, I'm not going to use those methods. I'm using some other methods, so it's not that important to collect respiration and pulse. If there's nothing else to take home from this talk, it's even if you're not wanting to use those methods, you should be collecting respiration and pulse. And it pretty much comes down to knowing what your volunteering is doing is essential. If you don't know what they're doing, if you don't know that they're taking spontaneous breath holds during your task, you can't correct for it, you can't account for it, you can't measure it. And I'll give you a few examples here of where I've seen this as an issue. So here's one paper published by Byrne and Murphy, where they were doing a word-non-word decision task. So they were just showing, in a block design, so these are the blocks, they were showing a bunch of letters on the screen, and the volunteers had to say, is it a word, is it not a word? This is not, this is not a high-stakes test. This is not challenge. This was not like tricky things. We're not like, dealing with, what abbreviations people put in tweets. This is, fairly basic words. But you could see how deep their breathing is. So this is averaged over the entire population. And during these blocks, the volunteers are breathing slightly deeper than when they are not doing the task. So, this paper itself is a fun paper. It talks about a bunch of ways to account for this, including this RVT, uses ICA and some other methods. But in the basic take-home message, again, is if we didn't collect respiration data, we wouldn't have known this was something we had to account for. Here's another example, which I'll call a minor confession. This is from my dissertation, where I had this lovely study that I published, which was a flashing checkerboard. Every 18 to 24 seconds, a 200 millihertz, so for 200 milliseconds, a flickering checkerboard appeared on the screen. Volunteers had to press a button and move their eyes. So I got, and it was, young and old aging, an aging study in eye field areas, in motor and visual areas. I was seeing the response magnitude and all this stuff. And, it's a nice paper. I like it. But the minor confession part was this wasn't the whole data set I collected. There's also the unpublished part of this data set, which was I wasn't just trying to look at these short responses. I was trying to look at the effect, was there an age effect with different duration stimuli? So if this instead of a 200 millisecond checkerboard, what happens if it's 3 seconds, 6 seconds, 12 seconds? So there's a bunch of papers out in the literature that show sort of how the response scales either almost linearly but not quite across this. Is this true with aging? So this was a big part of my planned study. The problem was a non-trivial number of my volunteers held their breath for whatever the task duration was. So if the checkerboard veered for 3 seconds, they held their breath for 3 seconds. If the checkerboard was 12 seconds, they held their breath for 12 seconds. And if you don't know, breath holding is possibly one of the most potent things you can do to cause a global MRI signal change because it causes massive blood flow changes across the whole brain. So I don't consider this, so some people talk about sort of the file drawer effect of not publishing null results. That's not really what we're talking about here, because this isn't a null result. This was a result that was hopelessly confounded by something I didn't plan on. So I couldn't. It's unpublishable because I couldn't say whether the effects were from my task or from the breath holding. So, but the thing to keep in mind is, if I hadn't collected that respiration data, I would have probably gotten beautiful data because you hold your breath for 3 seconds, you see one response. You hold your breath for 6 seconds, you see a bigger response. 12 seconds, you see a bigger response. I had beautiful results. The fact the results just had nothing to do with my task of interest, it had all to do with the breath holds. So again, this has nothing to do with all the ways to remove this data. This has to do with if you don't collect this data, you don't know what you're missing. And as I was putting together the slide, I had this one scary thought that came through my mind. There's a bunch of really phenomenal papers on this topic of different duration stimuli that are sort of fundamental to how we think about the field. Off the top of my head, I can't think of any of them published respiration traces or talked about respiration or talked about recording respiration. So if I'm in the mood, I might start harassing some of those authors and asking, and if I want to collect a really boring study, I can try and redo these with respiration traces and see what happens. But this is a fundamental thing with the field. We say longer duration stimuli scales. How much of that is biased by how people breathe? We don't know. Another example, hammering home the same theme. I was doing a task that was actually, the goal of the task was breath holding. And I wanted to do a breath hold. I had one block, one series of runs where people were doing breath holds, and one series of runs where people were looking at flickering checkerboards in a block design. And I used this technique called arterial spin labeling, which lets us get both the bold signal, which I think in previous lectures you've probably learned a good bit about here, if you didn't know already, and also getting a more direct measure of cerebral blood flow. And this is the classic response with this type of sequence. You see both the bold and the CBF go up during task and go down. If you want to see the scaling, CBF is increasing about 30%, while bold is increasing about 0.5%. This is what we expect to see. It's beautiful. This is exactly what a nice general ASL response. The trouble is I use the exact same parameters with a breath hold task. And my bold looks like what I've seen in a lot of times, where it sort of increases during the breath hold, peaks a little bit afterwards, and goes down. That's the blue line. But in this case, my blood flow measure increases up, and then it has these two gigantic peaks that are almost as big as the original. And we were trying to figure out what this was. And eventually we realized that when I do breath hold tasks, I like to alternate between paced breathing and holding breaths. And I strongly think that's a good way of doing things. If nothing else, because I'll say it caused my headache here, but it's also the reason why I found this issue. So I said, I wonder if it's the paced breathing. So what we did is we collected several minute runs where people just did paced breathing. So breathe in for 3 seconds, breathe out for 3 seconds, over and over and over again for a couple minutes, only a couple minutes. I saw a few groans in the room. Believe me, it's much nicer than breath holds. And this is what we saw. So the way ASL usually works is the blue data is our actual recorded data, and we collect what's called a tag, where you're sort of tagging the blood, and the control where the blood's not tagging. and it goes tag control, tag control, tag control. This green line is that breathing cycle, this 12 seconds of breathing in and out. And ideally, if you're not getting any neural effects, these two should be flat lines. Instead, we're seeing each of them goes up and down. So what we decided to do was collect this ASL sequence without any tagging at all. So now we're calling it tag control, but it's actually control, 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 control. And what you can see is every other volume is going up and down. And it turned out that whatever your baseline is, if you recorded an image while the chest was expanding, it was slightly lower. And if you were recording an image when the chest was almost at full width and contracting, it was decreasing. And the way ASL works is essentially the subtraction of these two time courses. So we were getting a chest movement artifact that was bigger than the ASL effect we should be seeing in the first place. And this is yet another example of another place where chest movement can really corrupt your data. And if you're not collecting it, you're not going to be able to identify what's happening. So I think I've almost hammered that message home enough. Okay, maybe two more slides. So when we're collecting it, just sort of as basic practical stuff, since I know a lot of people here will be doing this over the summer or much longer. For respiration, this is all set up at NIH quite well, but if you're ever other places, something to think about. Some systems, especially if you want to get that chest volume, some systems kind of auto-scale as you go. Make sure that isn't happening. And make sure that, from the beginning of your scan to your end, the values are consistent relative to each other. And obviously make sure the device is on stably. For cardiac, the typical pulse oximeters are really sensitive to finger movement. So taking time to make sure it's secure and telling the volunteer, try not to wiggle that finger during the scan makes a huge difference. So I'm not saying this is the only way to do it, but from my experience, I essentially usually put the oximeter on the finger, I wrap it with stretch tape, so it stays tighter on the finger, and then I put another piece of stretch tape here so that the wire holds still. Now, there might be other ways to do this well, but it's just something to keep in mind that just because the device comes with a little piece of Velcro doesn't always mean that's all you need to do to keep it stable. Particularly for MRI, a lot of these devices in MRI systems are designed for what's called gating. So most MRI systems include a pulse oximeter because they want to know where the beats are, because certain MRI sequences are what's called gated to certain parts of the heart rate. They don't care about stability. They don't care if they miss a beat or two. So they're not really designed to be as precise as the type of stuff we sometimes want to do in fMRI. And lastly, monitor traces before and during scanning. If things look weird, it's worth taking a pause and trying to fix them. The last thing on this specific area of topic is you can go beyond these simple pulse oximeters. There's been several people that have been using what's called near-infrared spectroscopy, or NIRS, to sort of go one up on pulse oximetry, where you're getting essentially you're recording more light frequencies from either a finger or a toe or multiple peripheral parts, and that gives you a better measure of total blood flow. Some of the main people that have been doing this is from Blaise Federer's group. And what you can see here is this is just a sample time series from this location here. You can see, can you see? Yeah, the dashed line's more visible here. So you can see the dashed line is bold and the solid lines are this finger trace. And you can see that there's quite a lot of similarity. There's so much that if you take this finger trace and you correlate it with the brain, you can see quite a lot of the brain is just correlating with that total blood oxygenation trace. So I think this is something right now that very few people do, including I don't do this right now, but it's something that I've been thinking is worth more attention as something to consider doing. One other peripheral to think about is eye tracking. So a lot of people think of eye tracking as a purely behavioral measure. And it is, but it also is a way to think about removing noise. So this is just one example study where in primates, Katie Chang et al. Showed that if you just look at sort of this, they had this attention measure of sort of when the monkey's eyelids were open versus closed. and they correlate with the brain, quite a lot of brain correlates with that across multiple monkeys. And one thing to keep in mind is, and there's other studies that show various measures of gaze and arousal attention also relate to the brain signal. And you might say, well, that's not noise, that's attention and arousal. Those are neural measures. But anything you're not accounting for is noise. So if you're trying to do a task scan and their attention is wavering in and out, that's a variable that you can account for that could make your study more robust. Similarly with resting state, if there's an arousal fluctuation, knowing it happens is useful. Now I'm going to switch to sort of things to focus on the participants. This hopefully doesn't need too much saying, but actually I guess the reason I put this first point up is there's a huge amount of discussion in this field on how to remove noise in post-processing. But the most important thing to keep in mind is the less your volunteers move, the less motion you have to remove in post-processing. And this is particularly important because head motion does systematically vary across populations. For example, this might shock people, but kids tend to move their heads a little bit more than adults. People with ADHD might move their heads a little bit more than people without ADHD. You know, this is not like on an individual basis, but by population, you're seeing these biases. So if head motion is corrupting your data, the more you can reduce that head motion, the more likely it's not going to cause problems in your data. And there's a lot of stuff to think about with head motion, but I think my main take-home message from here is whenever you attend your first scan, someone's going to show you how to hold someone's head still. And that might be a very good method for that study, but don't assume that's the best practice, because there really is no best practice. Best practice varies based on the population you're studying, it varies based on head size, and it varies over time. So head restraints is not sort of like a fixed thing that was figured out 20 years ago and everyone does the same thing. So just as two examples, around here we've started playing with these foam cushions that can be inflated, and we find those those have helped a lot with some volunteers. There's another group of people that have started marketing these custom molded foam coils, foam head restraints that are designed for each subject individually, that if you have the ability to make one for every subject you scan, have been phenomenally good at keeping head restraint still. So there's a lot of development, and something like this, these custom machine shapes might seem excessive, but if you're studying a patient population, if you're studying a rare individual and you get one shot at scanning them and they've never been an MRI before, the effort to do something like this might be well worth it. So these are things to think about, especially given there's the cost of a scan and there's the cost of a volunteer's time. And kind of sort of general things on participants is, when we're talking about reducing noise, this sometimes this is overlooked, but taking the time to make sure your subject knows what they're supposed to do and knows what it's going to be like in the MRI makes a huge difference. Sometimes it helps, sometimes it doesn't. But the more they know what to expect, the better. Also, the more feedback you get in the task, the better. So if you can collect reaction time, if you know they're answering things correctly, you're going to be a whole lot better off than if you don't know what they're doing in the scanner. Obviously, this is an issue with resting state scans, and that's where a lot of those peripheral measurements can help. And lastly, what I'm going to go on the next few slides is that noise is not independent from task design. So just to show you what I mean, this was a recent paper that is looking at sort of total displacement, so that's total head motion during scans, during a population that each volunteer did a whole bunch of different tasks. So the leftmost is rest, the rightmost is a go-no-go task, which is a fairly intensive task. And what you could see is and this is across several populations, and what you could see is actually, this may or may not be surprising, but subjects, when they're not doing anything, their heads will move more than when you give them a task that takes their attention. And that means that if you're really concerned with head motion, rest was for a long time looked at sort of like the ideal. You put someone in a scanner, you don't have to think about what they're doing, you get these magical results out. But if now what we're seeing is, but they move their heads more, that push towards a rethinking of like how we do resting scans. And I should say this isn't just with these tasks. So you can see the tasks vary, but even across age, if they take up the same data set, like we said, there is a actually, I was realizing, so earlier I was saying kids move more, but actually in this study, I think it's saying adults move more. Interesting. So maybe when I said it shouldn't be surprising that kids move more, I was wrong. What?
They're above 20.
Oh, they're above 20. Okay.
Maybe get a feature.
Yes. This is what happens when I'm still recovering. And just to show this is actually a finding that's been shown in at least 2 studies so far. So here's another study that shows the same thing. They were doing movement in resting scan. Here's children. Now you can see they move a lot more. You could see movement in resting scans. There's this visualization called Inscapes, which I'll call a super fancy screensaver. And then they showed them a movie. And what you can see is the more engaging the task, the less they move during a scan. So that's it for the first 2 sections. Now I'm going to go into, when I'm talking about removing noise during acquisitions, probably the things most people were thinking of was, what we're doing in pulse sequence and data acquisition. But that's only part of this, of course. Before I go into that last section, does anyone have any questions? Okay. So this is like I said at the beginning, this is a massive topic. I could put, an entire course in MRI physics could fit into this topic. I'm just going to sample a few different findings to start letting people think about what it means to reduce noise during acquisition. And I'll give a couple examples of how parameter choices matter. Some examples of how what we do before the actual acquisition scans can matter, or as that like sort of, yeah. A little talk about different contrast options beyond bold. Thinking about active motion correction and what a calibration scan is. So for general acquisition goals, there is no optimal sequence. Maybe like back in back in the ancient MRI days when everyone had a similar head coil and a similar limited set of pulse sequences, you were just going to sort of push for the shortest TR and the smallest voxel you can drive for. But now there's actually a whole lot more options on like what you collect and why. So, what you want to reduce for noise really depends on, do you care more about sensitivity versus specificity? Do you care about anatomical accuracy? About sensitivity versus specificity. That means like, is your main goal, you want to see a blob of activation? Would be sensitivity. And specificity is, do you want to, even if you might miss some activations, do you want to make sure your activation is in a really small area that you really expect to find it? How anatomically accurate do you want to see? How robust do you want to be against general artifacts? So, like for example, if you're doing a child-adult study and motion is an issue, you might care a whole lot more about using pulse sequences that are less sensitive to motion than in a study where you're scanning a bunch of healthy professional volunteers at NIH. And robustness against artifacts in general can bias, are you particularly, like I just said, like artifacts that might bias the study. And the other important thing to keep in mind is the optimal parameters aren't always obvious. So I'm going to give one example here, which is going to start with this question: what's the best flip angle for an MRI study? First of all, basic question: who here does not know what flip angle is? Okay, so I'll give a very brief answer. There are people here who have PhDs and 20 years of experience in the field, and there are people here who showed up 2 weeks ago at NIH for a summer internship. It's, that's the fun of this course. So flip angle is the first thing in sort of like the standard data acquisition model. The first thing you do is you have, you're in the MRI field, your protons are roughly lined up in one direction by being pulled by the static magnetic field. everything in MRI is about knocking them off that scanner position and doing, in a certain way and watching them come back. The knocking them off is called the flip angle. So the more you knock them off that initial position, the longer it takes for them to come back, and theoretically, to a certain extent, the more signal you'll get, because the longer it takes to return to baseline, the more signal. And there's a lot of nuance that I completely skipped over in that, but that's sort of a general definition of flip angle. So the question, so what is the best flip angle for a study? That is a great and incorrect guess. In fact, that's the exact guess I hope someone would say. So the Ernst angle is the angle. I didn't hear who said it, but thank you very much. That's the answer I was hoping for. The Ernst angle is depending on a bunch of your field strength and a bunch of other parameters. That's the maximum you can knock down. You can essentially knock things off baseline that will give you your maximum signal back when you return. So, for example, in this specific case, the Ernst angle would be right around here. And the trouble is, that is for signal to noise. It's not for temporal signal to noise. So signal to noise, like I said earlier, is sort of how clean your actual anatomical image is. So think about if you're collecting an anatomical image of a brain, and if you have lower signal to noise, it's going to look fuzzier and snowier. There's going to be just more speckling on it. So the lower your signal to noise, the more speckly your image is going to be. And the higher signal to noise, the cleaner the image is going to be. And that's important. But when we're talking about fMRI, we don't care about signal noise. We care about temporal signal noise. That's sort of how robust is it going to be tracking changes, whatever the value is at one location, how reliably is it going to be able to track signal that changes across time. And where this gets interesting is when you're increasing your signal to noise, you're increasing both the signal you care about and all these other all the other physiological measures that are also artifacts. So both interesting signal and noise scale with SNR. And what that means is even though SNR has this nice, beautiful arc with the Ernst angle right up here, TSNR is actually really flat until you get to the bases of those arcs. And what this means in practice is if you look at the hemodynamic response of, this is a basic flashing checkerboard task appearing for this period. What you can see is if you're looking at just the raw units off the scanner, as you get closer to that Ernst angle, your response shape is bigger, and as you get further from that Ernst angle, your response shape is smaller, but the shapes are always the same. And what that means is if you normalize them all to the same peak, these are essentially identical. And what your temporal signal noise is how fuzzy these are, so how much are they going up and down. And you can see it's pretty much flat from what, in this case, I think it's from, what does it say here, from 10? From 9-degree flip angle to 120-degree flip angle. It's almost completely and totally flat. So what this means is flip angle is remarkably irrelevant in talking about fMRI time series. And this is actually true. The flip angle is a good example of this, but this is true for a lot of sequences where we're talking about this gives us more SNR or less SNR. It all depends on how it relates. For fMRI, it relates to how it also affects TSNR. So there's sort of a bigger window on TSNR often where you have a little bit more give. And the irony of this paper, of course, is this paper, there are benefits to actually going to a really low flip angle. So you get less of what's called spin history effects, which could cause blood inflow and all sorts of artifacts. You can get better great white matter contrast. There's a lot of reasons to push this as low as you possibly can. But the truth is, even after publishing this paper, we're not wedded, when I'm publishing data, I'm not wedded to this, but I'll probably go here. I go here. I'm never going to push this to the absolute limit. And I can go into some details why, but even knowing this, I think there's sort of this innate worry that you don't want to rely on this a bit too much. Yes?
How does this change all field strength?
So what field strength is going to change is it's going to change the shape of this curve. It's going to change where the peak of that curve is also, so it changes the Earth's angle. And where these cross is sort of when your SNR gets so low that it matters. So the point where that happens is also going to shift. So at a higher, so this is at 3T, and at a higher field strength, your loss point I think is going to be a little bit higher. I'd have to think about that when I'm healthier. But still, there's going to be a huge flat area where it doesn't matter a lot. Yes?
Does field strength change TS? Does it change the TSNR curve?
It does, in a bunch of ways. So in addition to sort of changing the flat TSNR curve, it's going to change in any given voxel how much you get from large vessels and small vessels. So it's another example of how a lot of things interact with each other. And I should say, I'm not in the state to think about this on the fly, but the equations for this are pretty simple. They're in this paper by Javier Gonzalez-Castillo, and in some of these reference papers here. And if you want to look, if you want to look them up, you can calculate other scanner strengths and other factors pretty quickly. Other fMRI parameters. Voxel size, the smallest thing, you can say smaller voxels means you get lower SNR, but like we said, SNR isn't everything. You also get more anatomical specificity, which might give you higher TSNR of the stuff that you care about. Again, like there's going to be a point of diminishing returns. With TR, a lot of people now are pushing for as short a TR as possible. I'm a little bit skeptical at that. So generally, if you get a shorter TR, you're going to get lower TSNR, lower SNR. Possibly that's going to give you a little bit higher TSNR. I think there's some papers supporting that. It also means you can possibly filter out some high frequency artifacts a bit better. But one thing I think has been understudied is if those artifacts are removed by other methods, does it really matter? And it's still limited by the speed of the hemodynamic response. So your blood flow is only changing on the order of 5 seconds. So if you're collecting half a second TR, you're still limited by that. And the other thing with shorter TR and voxel size is the way people are really pushing this is with acceleration. And I will hand-wavingly define acceleration as collecting a data set where you're not sampling the whole space and throwing it into some sort of black box where you're estimating what's missing during reconstruction. And in some cases when you're doing this acceleration, you're getting lower SNR. It can give you the smaller TRs, smaller voxels. It makes multi-echo practical. I mean, acceleration in some form is almost the norm nowadays. But sometimes we don't think about quite what the negatives are. So it's just thinking in mind. It has the potential to remove some susceptibility, dropout, and distortion. If it's an acceleration that shortens your essentially data recording time, it could reduce some dropout. If it's something that can lengthen your readout time, then it actually could hurt dropout artifacts. But the important thing to keep in mind is reconstructions, you're estimating the fit. And if that estimate is off for many reasons, you're going to possibly create new artifacts or amplify artifacts that would have been minor. For example, like the chest movement artifact I was showing in the blood flow study potentially could be amplified if you're using any type of acceleration. Just to give you one example of an issue with acceleration is one acceleration for collecting a slice in less time is called grappa. There was, the way it's done is you collect a reference scan of the whole image, and that reference scan, so you collect it once at the beginning of the session, and then you use that information you collected at the beginning of the session to figure out how to best estimate reconstruction during the rest of the scan. So the conventional way of doing it was you're collecting sort of your lines in two readouts, and this is what your image would look like after reconstruction. But another way of collecting it using a reference scan using a flash scan gives you data that looks like that. So you can see between the two, there's quite a difference, all depending on what reference scan you used. And this is the type of thing that most likely, if you're an end user, this is not the type of thing you're going to be thinking about directly, what the best reference scan is, but it's something you should be aware matters. And just to give you an example, like if one of the lines in the reference scan are corrupted, you can get, it barely shows in this one, there's essentially some fat artifacts that are shifted through, and when those things are on the reference scan, it's going to sort of propagate through the rest of the image. Another example, this is using a sequence called a vaso sequence, which I'll talk a little bit more later, is, there's these little things sometimes in the sequence, is like something called fat saturation, which essentially means that most MRI we do excites water, and fat is excited at a different frequency. But because it's sort of off frequency, if it's going to get excited a little bit, but when you excite it, it sort of reappears in the image in the wrong place. So what you end up doing is, in some sequences where this matters, you essentially say, let's first excite the fat and kill that signal. So fat's not going to be excited when we then excite water. Renzo and I were working on some data, and we discovered that for this specific application, you did a standard fat saturation pulse with this vaso, and the data looked like this. And if you look really carefully, there's this little line here that you might have missed. But if then took the standard deviation of that time series, you can see that that line is massive. So that fat artifact was sort of exploding in the images with a typical fat saturation pulse. And when we essentially bumped up that fat saturation pulse, this artifact was reduced or removed. So little things like this where, like, if you know to look out for fat artifacts and you see it, that's your first step to say, okay, there's something going on here that we got to deal with. So what I'm going to talk about here is just, most of the stuff we've been talking about here is bold so far. When you're talking about noise, the contrast you use also matters. So different sequences are going to be more sensitive to your large veins versus your large arteries versus your small vessels. And this is a fun plot that Renzo developed to sort of emphasize that. So this is sort of different sequences, what they're most sensitive to. So what you can see is gradient echo bold, which is the workhorse of fMRI, is most sensitive to large veins compared to a lot of other stuff. So what's showing here is, if you follow this line, it's mostly blue with a little bit of red and a little bit of green. If you look at another sequence like spin echo bold, it has a lot more sensitivity to small vessels versus the other stuff. And Renzo's favorite sequence, vaso, which is a volume measurement, is much more sensitive to these arterioles and the small vessels, and almost not at all sensitive to the large veins. And the reason this matters is because the large veins are going to sort of wash out your signal the most away from what you're interested in, compared to sort of the small vessels or the stuff that's closest to the neural effects of interest. And what this means is, particularly if you're trying to push high contrast, you might have heard Renzo's talk the other day, you have the anatomical images at all these different contrasts, and then you have the functional responses. And you can see that depending on the sequence you're doing, you get much more specificity to that one area of interest. So for bold, you're getting things that are just sort of covering the whole cortex, and in between, which is mostly vasculature, while vaso is really sort of on that surface of just that cortex you want. And one way to think about this is, if you can put all these sequences, you can divide these up onto sensitivity versus specificity. And there is no right answer on this. So the reason bold is the workhorse of the field is it is the most sensitive by far of anything else we have out there, but it's not going to give us the millimeter or no way give us the submillimeter specificity we need. So if you're looking for an effect like, is my amygdala active in this task, gradient echo bold might be a great thing. If you're looking for, is my anterior amygdala active but my posterior not, then gradient echo bold is probably not the tool you want to use. Sorry for anyone here studying the amygdala, anterior versus posterior with bold. Another example of this is just another way to think of how things can vary is a lot of talks with acceleration has focused on what is called 2D SMS sequences, where you're essentially simultaneously collecting a pair of slices at a time and filling in space. And another way to do this is collect essentially the same amount of data, but you're just sampling across a whole 3D space over time. So like as you add more data, you can see is this the first image still going? Yeah, so you see the first image sort of adds in detail over the whole thing. This is just filling in slice at a time in full detail. And what's interesting about this is the reason people like 2D SMS is if you're talking about bigger voxels, and you look at your TSNR, the 2D SMS sequences beat out 3D sequences at bigger voxels. But if you really want to push your small voxel size, so if you're going sub-millimeter, suddenly your 3D EPIs are actually winning. So this is again an example like how your optimal sequence, if you're collecting 2 millimeter cubic voxels, might be different. It would be significantly different if you want to collect 1 millimeter cubic voxels. And just to give you a sense of what this looks like, you could see at 3 millimeters, this is what they look like, versus at sub-millimeter. You could see that you're actually getting kind of a nice cleaner thing with that 3D sequence than the 2D. Last few slides. Another thing to think about is going back to the topic of motion. There's a lot of ways to correct motion during the scan. So the example I'm showing here is called a promo sequence, where before each image acquisition, you're collecting what's called a navigator image, which you can use to say, oh, the head moved, and then you essentially correct for head motion in acquisition, and then you collect whatever you're doing next. And what that means is you can see all the, it's not the greatest image here, you can see all the ringing in this image here, but when you use this active correction, it cleans up a whole lot. And I should say this is one approach to doing this. A lot of other approaches do real-time motion correction using external measures to either sort of markers on someone's head or cameras or other methods. The last general topic to think about is calibration scans. So or baseline scan. I define this in general as collecting an additional scan that helps correct for subject specific variation. So this actually goes back to the first minor confession study I was showing from my own work, where I was showing the responses to that flash and checkerboard task in young and older. But in that same study, I also collected a hypercapnia, a breath hold task. And I showed that in these same areas, there is variation in young and old, how much the response changes to this global change of breath hold. And when I use this information to correct this, you could see that the task-based corrections still varied. These no longer cross significance, but we are still seeing a robust effect in the most significant areas. So it's a way to correct for a potentially population-specific biases in vasculature. There are other examples of baseline scans, either simple tasks, just to say like, we know what their basic visual response is. You can do other more complex forms of calibration using, CO2 breathing, enriched O2 breathing. There's baseline CBF scans. There's other people have done standard deviation arresting scans. In general, I would say these are all can be very good sanity checks, and they might be very useful. The minus is if you're collecting 5 minutes or 10 minutes of a calibration scan, that's at the expense of something else. And push comes to shove, when that expense has limited, until there's sort of a true killer app, it's limited the applicability of this. I hope that will change, but we haven't quite reached that point yet. So generally when someone says, do you want to spend 10 minutes on a calibration scan, or do you want to collect 10 minutes of your task of interest? Most people choose a task of interest. So I'd say there's very few data in sort of clinical populations that have really effectively used these so far, but we'll see. And in summary, if I haven't said this enough time, noise from many sources will always exist in fMRI. And the more you understand the sources and what affects them, the better you can control for noise in acquisition and correct for noise in post-processing. Okay?